Welcome to the 2023 Earth Science Week webinar series based on our theme, Geoscience Innovating for Earth and People. We have with us today speakers who are experts in photogrammetry, an innovation that can help create both digital and physical models of Earth's features on varying scales. These allow geoscientists to do things such as view fossils in much greater detail, and to model volcanoes and other large features, including making simulations that allow geoscientists to test changes in environmental conditions. For more detail on how photogrammetry is done, our first speaker, Ryan Hollister, will give an introduction to the process.
Hi, everybody. My name is Ryan Hollister, and I am an adjunct lecturer in the Earth Sciences and Geology at Modesto Junior College and California State University, Stanislaus, here in the Great Central Valley of California. I've done photogrammetry for about 7 or 8 years now, and I'm not the end-all be-all expert, but I hopefully can show you some things that maybe demystify the process of what it takes to make these models. And then in a future video, we'll talk about how we can implement these 3D models in an educational setting. So here you go, to a brief introduction of photogrammetry for geoscience educators. So we'll talk about what is photogrammetry, what are the basics of how it works, and then what are the tools you need and some of the products that are made from there. So basically, photogrammetry is, if you take a look here down at the bottom left-hand screen, it's the process of creating a 3D computer model like of a rock specimen or a landscape or any object using a series of several hundred photos or more of that subject taken at slightly different angles. And then that's what I was doing in that picture of a nice granitic glacial erratic atop Sonora Pass back in 2016. But when you take all those images that are slightly overlapped, the computer then can use some pretty amazing math and geometry to triangulate where in space the cameras are to create these cool 3D models. So how does it really do that? Well, let me show you. So first things first is it takes those paired images or images that are very near one another that are from slightly different angles, and computer programs like Agisoft Metashape find matching pixels between these different images. So for example, if there's a feldspar crystal here and there and some lichen down at the bottom, it will take those and match them up and tell the camera, hey, these are the same pixels, just in a different image, and this is where it's shifted in space. That was hand-drawn. On the not hand-drawn side, this is what it actually looks like in Metashape, and the images here are on top and bottom instead of left and right, and it just looks like a bunch of gobbledygook until I zoom in here, but the blues are showing lines where one pixel is matching another with some high degree of certainty that the computer says, yep, this is a match. The reds are ones we just kind of toss out. So once we know those matches, that's the zoomed-in version on the right-hand side. Once we know those matches, the computers usually use parallax between those two matched pixel groups to calculate where those cameras are in space. And so this diagram kind of shows you really quickly how it's done, where if you imagine the yellow and green are pixels on a rock, if I took an image from over on this side of the rock, the yellow and the green would end up on the left side of the picture. If I took a picture of the rock from the center here, you would see the yellow and the green are kind of in the middle. And over on the left-hand side image, the pixels end up on the right-hand side of the actual produced photograph. And so based on where those computer knows those are the same pixels, but they've shifted in the frame, it can calculate based on that parallax where the cameras are in space. And what you end up with is a really cool three-dimensional outline that shows you where the computer thinks my pictures were taken to make, and after they've been aligned just like this, so you can kind of see where they are right there. So that's called camera alignment. After you align your cameras, the next step in photogrammetry to make the model is we got to make these point clouds. So the cameras we now know where they are. Now what we have to do is take those pixels within the images and put those pixels based on the parallax and triangulation, put them in a three-dimensional coordinate system. And so it starts out first with a sparse point cloud, which kind of gets things organized and doesn't take as much computing power. And so what you see here is 96,000 points that kind of look like a swarm of bugs or a cloud of bugs. And this is where it gets its name, point cloud, from. And from that, you can do lots of other things and then do a more intensive processing to create what we call a dense point cloud, which is 40 million points. And by having a more dense point cloud, you're going to get a better model, and I'll show you how in just a minute. And even though this looks just like an image, it's actually, if you zoom in here, individual points that have been aligned in a three-dimensional space, okay? So these next step then is to take all of those points and turn them into a surface. And so it's kind of like Pee-wee's Playhouse. If you ever watched that growing up as a kid, connect the dots, la, 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 right? Well, if you connect those dots or averages of where those 40 million dots are, it can create these polygonal surfaces called a mesh surface, which basically is the outline of the entire object there. And so all those polygons at different angles can do a pretty good job mimicking where the surfaces of an object are in space. Think of it like chicken wire, all right? And in this picture, there are over 1 million polygons or 1 million faces, triangles and squares and such. So then the last part of photogrammetry here, or the second to last part of photogrammetry, is we take that chicken mesh, that chicken wire, that mesh, and we got to do like a digital paper mache over the top of that wire frame or that mesh. And so what you can see here is if I zoom in, you can see the polygon still, but it's now filled in. And so the computer is able to calculate where the solid surfaces should be, what should be hollow, etc. And you get a pretty good representation of what the area looks like. So that's the three-dimensional model. It doesn't really look like a rock yet. So that's where you got to, what we do something called texturing, which is taking those images from the cameras. And now that the computer program knows where the camera is in space, it can take those images and say, hey, the camera was looking here, stick that picture right where the camera was looking, and it pastes them and glues them all together and makes a coherent, cohesive picture that then gets wrapped around and stretched around that skin and makes it look like an actual three-dimensional model. If you were to unwrap it, this is kind of what it looks like. It looks a little funny, but the computer knows how to take this file and then stretch it back around the model and make it look exactly like the rock. So some of the photogrammetric programs also have scale, where you can embed, either you can take a picture of the scale or you can just measure it. And once you do that, you can actually give quantitative measurements from those models, which is very useful for students, say. All right. Some of the programs have that baked in if you use LiDAR. Otherwise, there's some other workarounds that we can talk about a little bit later on. Now, some of the tools you need if you want to get into photogrammetry, you obviously need a camera, you need a computer, or you can have a camera and a computer in your pocket, which is the smart devices. And these smart devices have kind of democratized making photogrammetry accessible for everyone, which is awesome. But if you really want the high detailed stuff, you still got to kind of rely on cameras and computers, which can be a little pricey here and there. So speaking of cameras, the more megapixels you have, the more processing time it takes, but the more detail you'll get in your resulting models. My camera now is 45 megapixels. The one I used to take that boulder at 2016 was 24 megapixels. So it just depends on what you're looking for. Camera phones, 12 megapixels, those work pretty doggone well too. And they're pretty quick. But anyways, you can take those cameras, you can use them in a studio setting, which takes more investment for lights. You can do in outdoor settings, or you can even have cameras mounted on drones if you want to get a larger subject area. And sometimes these can be multispectral too, so you can get things more than just what's visible wavelength, which is pretty awesome. And in terms of computers, like I was saying, this is the computer I bought in October to help me do some of my models. $6,000 is a hard ask for a lot of folks, and this was out of pocket as well. But when I'm doing it for part of my little side businesses and also making models for the greater geoscience world here, you need a computer that has a beefy video card and things like that. That's where most of the processing takes place. And just to give you an example here, comparison, 2016, it took 17 hours to make that model. I used the same exact photos in the same modeling program. And right now in 2023, it took 32 minutes to make. So things have improved. And even in my really intense models these days, don't take more than 10 or 11 hours at most to create, which is pretty great. And so I create all my models in Agisoft Metashape. It has an academic and educational value. I think it's like $180 for a license for folks to use that. That's pretty inexpensive compared to what some of the others are. There are actually lots of free apps on smartphones that you can use as well. But if you really want to get into this, you can drop me a line and I'll show you my contact information at the end, and we can get into that into more detail. But as I was saying, the smartphones here are the things that kind of democratized it all. And in 2020, Apple introduced the LiDAR on iPhone Pros and iPad Pros. And there's the LiDAR button, right? Or not the button, but the where the LiDAR comes out of. And you can use apps. And I prefer Scaniverse and Polycam. Those are the two apps that I use quite frequently here. And it kind of skips a step in the photogrammetry where it actually uses LiDAR to scan everything. And then it uses the gyroscopes in the camera to know where its position in space is. And if you press play, this is directly from my phone a few hours ago, you just basically scan over where all the candy cane stripes are. And that helps you know what you need to scan, what hasn't been scanned, and where you have been already. And so you just scan all that done. And once you get done with that, give it another 2 or 3 minutes to process. And this one actually took about 85 seconds to process on my phone. You get a really cool model of my columnar basalt lamps that are out in my front yard here. So phones are very fast, very efficient. And what you can see here is basically it takes a scene, like in this case, an angular unconformity in Washington State on, I think it's Beach Ford, Olympic National Park. And this is basically what the LiDAR makes, is it makes the solid surface first, kind of skips the mesh and all the other kind of things, makes a solid surface, and then pastes those images right on top of the surface. You can see when you zoom in, there's a few artifacts of my sun, and some of the conglomerate here up on the top is a little bit like smeared and things. But from an educational standpoint, you can use this and measure it and do all sorts of cool things. What a great tool to have. And it only took like 8 or 9 minutes to create. Pretty amazing stuff. If your phone is not an iPhone, or you do not have LiDAR on your phone, because there's not very many Androids to my knowledge that have LiDAR, you can still use those apps like Scaniverse and Polyscan to take a bunch of photos and then upload it to their server, cloud server, and they process it and create photogrammetric models that way for you. And for the most part, they're free. If you do it, you get so many free ones a month, which is pretty slick. So we've come a long ways in terms of 3D models from 2016 to have like these hollow Haida keys to more accurate and precise and sub-millimeter resolution, which is pretty amazing stuff on like these desert roses. So these are some of the products and the results of photogrammetry that we can eventually incorporate into our classrooms. High resolution, detailed hand specimens. You can get large areas scanned with your phone or with other cameras, like I was telling you, and you can measure offsets of creeping faults, let's say, like this one in Hollister, the town of Hollister. You can use drones and create huge digital elevation maps, or like stratigraphy based on different areas using a drone to take pictures of it all. And in this case, it's like a 340 meters from the little creek up to the top. So this is a scale much larger than I typically work with, but I'll show you in another video series here where you can find all these housed and how you can incorporate that into your classes. You can also use, you never know, you might need LiDAR and photogrammetry for insurance claims, like when wind storms destroy your friend's neighbor's car, and you can submit that to insurance claims, which I thought was kind of interesting. But I think one of the most useful things that you can use it for is STL files, which basically take the 3D model you made on your computer, and you can then 3D print it. So if you have students that need tactile interaction with objects and models, you can print them if they're delicate, if they're fragile, and you don't have to worry about them breaking them. This is the desert rose right up here that you can see. And this on the video here, or on the screen, is dinosaur coprolite that we don't really want too many hands touching. So in case you didn't know, Google Earth also uses photogrammetry for its 3D cities and landscapes in some of the national parks that are more higher resolution. This is photogrammetry as well. So I'm sure you're wondering, how do I incorporate this into an educational setting? We'll discuss that in the next video. But until then, if you need to contact me, there's my information. If you scan the QR code, it'll take you to my Phaneritic Sketchfab page where you can see many of my models that I've posted, and we can go from there.
Thank you, Ryan, for your detailed description of the process of creating photogrammetric models. Next up, we will hear from Dr. Jeff Moore from the University of Utah. He will discuss some ways in which geoscientists can use photogrammetry to make digital models of geologic features to better understand Earth's processes.
Hello, everybody. My name is Jeff Moore. I'm a professor of geological engineering here at the University of Utah in the Department of Geology and Geophysics, and I'm here to talk to you today about geoscience applications of photogrammetry, and specifically our work at Rainbow Bridge, Utah, which you see in the image on the screen. Just first, a little bit of background about Rainbow Bridge. It was established as a national monument in 1910 under then President Taft. It is one of the world's largest natural bridges with a span of 275 feet and a height of 290 feet, so truly exceptional scale. And it sits aside Lake Powell, which straddles the border of Utah and Arizona. At full pool, Lake Powell would actually extend underneath Rainbow Bridge, which it has done in the past, and but that hasn't been for several decades now. And Rainbow Bridge is a sacred site for Native American tribes of the Four Corners region. Normally, to reach Rainbow Bridge, you would take a boat from Page or from Wahweap Marina and come up the lake and turn off at Forbidden Canyon, and then take a short hike to reach the national monument. So photogrammetry at Rainbow Bridge first started in 2015, led by Jack Wood, who's with the National Park Service. And Jack, who you see in the image here, took hundreds of ground-based photographs of Rainbow Bridge, and these were GPS tagged to have the specific, precise location for each photograph. Just for scale here, you see, people standing in the area where Jack's standing, and then this is Rainbow Bridge itself, and that's actually me on Rainbow Bridge. So just for a sense of really how truly massive this feature is. So Jack had created this really beautiful model of Rainbow Bridge using these ground-based photos, and that's available on the Park Service Sketchfab site at this link here. And so this is just a screenshot of that beautiful model. The problem was that because all the photos used were ground-based photos, there's actually parts of the bridge that you just can't see from the ground. So however wonderful and beautiful this model is that Jack created, it's actually missing parts of the bridge that you couldn't, that he couldn't photograph from the ground, even using the camera mounted on a long pole. So my team actually returned earlier this year, and because you can't fly a drone in National Park Service lands, we used this helium balloon setup where we dangled a GoPro beneath this, large helium balloon, and could then control the GoPro from a smartphone and take images, specifically these views of the bridge that we couldn't capture from the ground. And so then the idea is that we'll be able to combine these photo sets. We have Jack's original photo sets and our new photo set from 2023 to capturing these really specific areas, and then thus completing the photogrammetry model of Rainbow Bridge. Here you can see one of those images. This is the shadow of our balloon. I like that. And this is part of the bridge that we really couldn't see from the ground. So though, to the application side, what do we do, my team, what do we do with photogrammetry models? And what we've been doing for the last decade or so here in Utah is vibration analysis of natural arches, bridges, and rock towers. And the basic question that we ask is, what are the natural modes of vibration of these landforms, for example, Rainbow Bridge? And the reason we do this is really twofold. The first is for structural health monitoring, which I will explain. And the second is broadly for vibration risk assessment. So asking, does this energy source, could that excite, high amplitude vibrations of the arch or tower that could cause damage? And we do this using a combination of two approaches. The first uses in situ ambient vibration measurements. That's what you see down here in the images. So for this, we use a seismometer. Here you see our seismometer. Very sensitive instrument, very expensive instrument, used normally for measuring earthquakes. We place it on the arch being assessed. Here's landscape arch. This is another arch within Arches National Park. The instrument's just under this bucket. And we leave it there for an hour or more and just collect this ambient vibration data. That means we don't, excite the arch in any way. It's just ambient motion. The other thing that we do then is numerical modeling. And so we extend our data by using numerical models. And here's where the photogrammetry really becomes important. It really sets up accurate numerical modeling. Just a really brief, quick primer on structural dynamics. We've known for 100 years of measurements or more that all man-made structures on the Earth's surface are constantly vibrating. So think of a tall building, and here you see the example of the Campanile Bell Tower on the Berkeley campus. These tall buildings are swaying back and forth. Bridges are bouncing up and down and moving at these complex modes, and these are what we would call their natural modes of vibration. So here you see the bell tower is swaying back and forth in the north-south direction and also in the east-west direction. And this is happening at a frequency of 0.8 hertz. So hertz is once per second. So that's 0.8 times in 1 second. It's completing this motion. So the natural frequencies for these modes are really simply controlled by two things: the geometry of the feature and the material properties. And it's really the geometry where photogrammetry is key. So now using photogrammetry, we can capture very accurate geometry. We can create very accurate geometrical models of even complex landforms like natural arches and towers. And here you see Castleton Tower. It's located in Utah, sort of near Moab, and it vibrates back and forth, much like a tall building, at about the same frequency as the bell tower on the Berkeley campus. So the big idea is that by measuring, modeling, understanding these vibrational modes, we establish a vibrational fingerprint, or in fact, a structural fingerprint that is unique to every landform. And the procedure of measurements and modeling and understanding these natural modes is what we call modal analysis. And here you see numerical results for Castleton Tower showing, that swaying back and forth at 0.8 hertz in one direction and at 1 hertz in another direction. So 1 hertz is 1 time per second it completes this swaying motion. So at Rainbow Bridge, we conducted this in situ ambient vibration measurements. Here's an example. We're seeing two instruments here. One we placed on the bridge, that's station code RAB-C, and one's on the canyon floor, that's station code RAB-D. And you see them over here, but we're looking at these in a frequency spectrum. So think about it like a sound spectrum. If I pluck a guitar string or strike a piano key, you hear not just one tone, one frequency. You actually hear a combination of many tones. So you have what's the fundamental, that's the lowest, but then you have a number of overtones. And natural arches, bridges, and towers actually do the same thing. So here we see the fundamental frequency of Rainbow Bridge, or the lowest natural frequency, is at about 1.1 hertz. And we see that on the two. This is the north-south component of motion, and this is the east-west component of motion. Next mode comes at 2.2 hertz, 2.5, 4.2, and so on. We have all these natural frequencies represented in this ambient vibration data. So the idea is that Rainbow Bridge is vibrating all these natural modes all the time, every second of every day. And through this procedure of numerical modal analysis next, we want to understand what those modes actually are, what they look like, what the displacement, deformation patterns actually look like. So this is now where the photogrammetry models are key. They establish this very accurate geometry for every arch or bridge or tower that we measure and assess. And so here you see Rainbow Bridge. We have the model that Jack made. And so we had to, complete that and turn it into a solid. Once we did so, we could then trim away the extra parts, and import that into a numerical analysis program where we ask the program, given this geometry, given these material properties, what are the natural modes of vibration? What do they look like? What does the bridge want to do? And the program can very efficiently solve this for the complex geometry that's established by the photogrammetric model. In doing so, we establish this modal analysis. Now we know what the frequencies are of vibration, and we know what the deformation patterns are. So here we see the first several modes of vibration of Rainbow Bridge. Of course, the displacements are greatly, greatly exaggerated just to help visualize them. The point again is that the bridge is doing this all the time. Every second of every day, it's vibrating at the combination of all of these modes together. But using this procedure of modal analysis, we're able to pull them apart and say, okay, here's the first one, second one, third one. Here's what they look like. Here's what the bridge is doing at those modes individually. And again, that's very much like a guitar string or a piano key. If you pluck it, it's doing all those modes together all the time. And you can use this procedure of modal analysis to understand what they are. So why do we do this? The main reason we do this is for this idea, this concept of structural health monitoring. Structural health monitoring is a relative method where once you have established a baseline measurement, this vibrational fingerprint or the structural fingerprint, you can come back and measure again and look for changes in that structural fingerprint. And if you see changes in the resonance frequencies, then you have evidence supporting the hypothesis that you have structural change. So first you have to establish this baseline modal analysis, and that's what we've done in the preceding. Now you can come back at some interval. It can be a regular interval. Here we did it every 2 years. We see the original data from the red curves from what I previously showed, and then from data from 2017 and 2019. And if we look at this, we can see, okay, that there's no discernible change in these resonance frequencies. This vibrational structural fingerprint has not changed. So we can report back to the Park Service in this case that during this time interval, there's no discernible adverse structural damage or change to Rainbow Bridge, which is a good result to be able to say, especially given that these curves, these green and blue curves, that data just takes an hour to generate. And so it's like a checkup. It's like a really brief checkup that you can now make at any time down the road. Say there's an earthquake, we could come back and make another measurement. So, but from our original data here, we see no change. This is the idea of structural health monitoring, and me and my team have been doing this on tens of natural arches around southern Utah, some of which are really iconic and culturally valued landforms representing the area and also sacred features for Native American peoples in the region. So the other main application that we use these data is for vibration risk assessment. This is a very big and deep field. I don't have time to go into it here, but the basic idea is that we get asked, and land managers ask very difficult questions from time to time, like a helicopter, for example. A helicopter creates infrasound from the main rotor, and they have asked, and I have been asked, can this infrasound excite resonance of natural arches? Well, if the frequency of the infrasound energy precisely matches the natural frequency of the arch, then yes, it can. And we've measured this, and people have measured some high amplitude motions due to nearby helicopter flights. And so you could ask the same thing about trucks driving on a highway or trains passing nearby, or of course, natural phenomena like earthquakes. I think one of the interesting side outcomes from these photogrammetry models is that they actually established this really enriched digital archive for a natural arch. So here we see what's called Rainbow Arch. Coincidence that the name is the same. It's Rainbow Arch rather than Rainbow Bridge. Rainbow Arch is a very small but very beautiful arch located in Arches National Park, and it actually collapsed sometime in the winter of 2018. We don't know why it collapsed, how it collapsed, nobody witnessed it. But before it collapsed, we had created this photogrammetry model. And so now we have this a 3D representation of the arch, not just one photo from one angle. We have this really accurate and beautiful 3D representation of the arch. So it lives on in this archivable sense. Another thing that we do from the photogrammetry models is that we can use these to do static stress analysis. We can analyze the stress conditions in natural arches. So rock as a medium hates tensile stresses. Rock is very weak in tension, is very strong in compression. So a good form for an arch is one that minimizes tensile stresses. And we know from 1,000 or more, that thousands of years of human engineering, that an ideal form for an arch to minimize tensile stresses is what's called an inverted catenary. And this is a form which you could like dry stack an arch, in which people have been using to create masonry arches for thousands of years. So what our stress analysis shows, that Rainbow Bridge has naturally self-sculpted and evolved into this really beautiful inverted catenary form that minimizes tensile stresses and holds the weight of the arch in compression where rock is strong. Flatline arches, like here you see a Watchmo Bridge, like a flatline beam on the other hand, have very high stress concentrations, both tensile and compressive stresses. And these are areas where fractures will localize and propagate, and where the bridge might ultimately fail. So Rainbow Bridge has self-sculpted, self-achieved this really beautiful, ideal stress-based form of the inverted catenary. That's the good news. The bad news, also revealed by our photogrammetry model, is the bridge is actually leaning outward a bit. And this is a result which shows these, the sort of gravitational self waves, not just pointing downward, it's actually pointing outward a little bit. So the bridge is actually trying to topple over. And we can see evidence of that in the field. We have this large tensile crack separating the bridge from this adjoining bedrock knoll. And so the bridge might actually end up failing by falling over. We don't know. As an aside, last fact, random fact, photogrammetry model also told us that the Rainbow Bridge weighs more than 100,000 tons. For reference, that's as much as an aircraft carrier. Okay, so just to wrap up, my group uses photogrammetry and photogrammetric models to support vibration analysis and risk assessment of natural arches and towers here in Utah and other culturally valued landforms across the world. We also use these models for stress analysis, especially studying arch stability, their long-term evolution, and modes of what might be ultimate failure. And lastly, I'll point out that these photogrammetric models make for excellent archivable media and a really convenient, interesting way to digitally share unique views of these unique landforms. So I will leave it at that, and thank you very much.
Thank you, Dr. Moore, for showing us how photogrammetry can be used in the geosciences. We will now hear again from Ryan Hollister as he describes how photogrammetric models can be used in earth science classrooms to engage students with the NGSS science and engineering practices. He also discusses how to create virtual field trips that provide context for photogrammetric images used in lessons.
Today, I'm here to talk to you about some things that are pretty near and dear to my heart, and that's ideas and resources to help you meaningfully incorporate all these really cool photogrammetric models you've been seeing, we've discussed about building. How do we successfully incorporate those into the geoscience education setting? So the quick roadmap for today is I want to set you up with some pedagogical thoughts on how to utilize these models and pretty much technology in general in the geosciences. Then I'll show you some of the uses of how I've used photogrammetry in my classes. And then at the very end, which is something I'm sure everybody's looking forward to, is where you can find the model resources that you can freely use. So things like petrified wood or fossils, rocks, minerals, landscapes, all sorts of amazing things. I'll show you where you can find those. So to start with, the technology is dazzling, right? But it's just a toy with limited educational value if it's not appropriately implemented in an educational environment. It's just a rock is just a rock here. I mean, you can look at it, it looks pretty, but so what? So as teachers and educators, we got to figure out what are those steps that are needed to harness the power of those photogrammetric models, and how do we make them educationally useful. And you can see some of the first ways I went about doing this, and still do it, is making photogrammetric models and having students notice and wonder and make field sketches as if they were actually there in person. So I actually have a couple of steps that I start with whenever I'm making new resources for myself or collaborating with other folks. I want my models to be made for a purpose, and I want that purpose to allow students to discover something, discover a story. So for me, models need context and they need a purpose in that educational setting. So as an educator, need to know what is the end story that you want these models to help tell. Maybe the model is one piece of a story. Maybe it's the entire story. I don't really know. But you want to allow a way for students to use the models to discover these results. So it's not just somebody telling them what's happening. Help them find a way to discover the results. And I also like emphasizing collaboration when I do all of my exercises, even at the university level. Low stakes collaboration is a pretty great way to go about things for me. And what you see on the right-hand side, that is the final story that I wanted my students to know after taking a large immersive virtual field experience that had lots of photogrammetric models embedded in there. So once I knew what I wanted them to know, then I had to figure out, how am I going to let these models do the talking for me, and how can they let students discover that story. So one of the things I always ask myself in order to incorporate that, like, how am I going to let students discover something? Well, I always got to constantly ask, what skills and strategies will they need? Will the students need, or will they need to develop to successfully do that discovering and to successfully do that collaboration? And so the second step I always rely on then is utilizing the science and engineering practices of the NGSS. And I'm not going to go too deeply right here, other than to say that a huge majority of the states K through 12 in the United States have adopted framework based on the NGSS. And one of the key pieces of the NGSS are these science and engineering practices. They want students to develop a bunch of these science and engineering practices because it's what scientists and engineers do on a daily basis. So for me, when I'm building my models and when I'm building my field trips and things like that, I want my students to be asking questions and analyzing and interpreting the data from those things, maybe using mathematical and computational thinking with those models. How can they then construct explanations based on what they're seeing? So these are the ideas and tips and tricks that I always rely on to help me, in my mind, scaffold the tools that I'm going to be giving the students to help them discover these really cool things with the models. So that leads me into the example portions here of how I've used these in my career. So I've used them in college courses, professional development, high school, elementary classes. The models are great. It just takes age-appropriate scaffolding, age-appropriate questions, and age-appropriate expectations to make these successful. And so what you can see over here on the left-hand or right-hand side are a couple of models that second grade students were using and observations they were making that would then lead in to help tell a story of glacial erosion, which was pretty cool. So how did it all start for me? I made my 3D models originally to be embedded in a much larger immersive virtual field experience. I wanted the students to be able to go to the field, pick up the rocks, explore like they were there in person. And so that's how it originally came to be, is I embedded these photogrammetric models inside a larger 360 tours here. I think there are 7 or 8 different stops, and I think I made 9 or 10 different models, but it allowed folks to zoom in, zoom out, pick up the rocks, explore them. And then I also created a huge amount of field guides that would help them understand and interpret what they were looking at. So this whole time, students were analyzing and interpreting data, trying to eventually piece together things that would collaboratively develop and tell a story of how the columns of the giants were created here up in the Sierras. Now, the upside of that is it was a really cool collaborative learning experience, right? Having all those models and things like that. But it took months to create. So it turns out that there's a much easier way and much more accessible way for most folks of how to create virtual field trips easily, quickly, and with like free tools that you don't need to learn how to develop. And so Google Earth Web for me is like the #1 thing now that I make virtual tours on and embed photogrammetric models in. And it's also something that I have my students do quite frequently. So I'm just going to pop out here and show you kind of an example of rock samples. Like when you fly into different sites, you might have a 3D Google Earth view like this, or for one site, in this case, I'm wanting my igneous rocks to tell a story or have my students kind of identify what type of igneous rock it is, and then identify the story eventually of how it was formed. But you can fly into these street views like this, and if you click on the link right there, it'll pop open. Oh, hey, look, it's the 3D model that you've been seeing all through the presentation so far of that chunk of granodiorite that was literally taken about 15 feet from where this street view was taken. So it provides context and it helps provide a story of what's going on here. And once you have enough rocks and you've looked over there, students then can collaboratively put all that information together to figure out what in the heck happened here, geologically speaking. It's pretty interesting, right? I think it's pretty cool. Not that you need my endorsement for my own materials. But if you don't have Google Earth or you don't want to learn how to use it, you can also use the models from Sketchfab, which I'll explain more a little bit later on. You can take those models and copy links and embed those within like Canvas or Moodle or your class websites, or if you have your own websites. And what I do is sometimes I'll put them side by side, models next to street views that you can also embed from Google Maps. So it's another way of embedding these models and bringing the models to life with a sense of place from where they came from. Also, there are ways to turn off the labels if you're curious, like if you don't want to give away what the answer is, there are ways of turning that off. I just forgot to do it for that example. So another way I use virtual models embedded within those virtual field experiences is now I can also have quantitative measurements using the Polycam app and using scans from my phone on LiDAR. And if you go to those websites, it's pretty slick and pretty amazing too, where here's that Zabriskie Point, the ripple marks here that were exposed this past February in some really strong rains. But now, you know, students can measure how big is the bed, how big are the ripples, how thick are these beds, and it can help, you know, interpret and tell a story about the past environment that was here before it was tilted up. And you can even put these into some programs where you can measure the dip and angles and all sorts of amazing things with it too. So quantitative is a way that you can go should you desire. Just what do you want that data to end up telling? What story do you want students to discover with that data? Models can also be used and screen captured and annotated by students. And so they can fly into those areas, and I'll have assignments where they just need to screen capture and, you know, annotate. Oh, here's some cross-cutting relationships, which happened first, second, and third. And they can do that and then submit that as part of their collaborative work outside of class. You can do it within lab too, if you want, but these days when we're back in person, I want more hands-on stuff. And then we can use this as these tools as a way to reiterate or practice at home. So models can also be screen captured and annotated. Like I was saying, there's some imbricated river cobbles. We just have no big rivers near us. So being able for students to kind of play around and zoom in around like these river cobbles to be able to, doesn't look like much. And then you finally hit the right angle and you can see, oh yeah, looks like all those rocks are laid in a certain way. And so we can talk about river flows and things like that, which is pretty great as well. All of those, by the way, go in to tell a larger story of, you know, the river process that we are looking at. So the last way, or not the last way, but another way I've always used these 3D models here in the last few years is to print them, 3D print them for folks and students that have low vision that need to interact with it tactily, and maybe the specimens are a little too fragile to have lots of hands on it. So I've 3D printed them, and it's, you know, it's plastic. It doesn't have the same density or anything, but it's a pretty good way to feel at least the outside texture. And there are, believe it or not, there are new 3D printers that have bubble jet inkjets on them that can 3D print a semblance of the photograph that overlays this and can print it on the 3D model as it's being printed to make it look a little bit more photorealistic. It's not the best yet, but it's there. And then I think one of the most novel ways that my photo scans have been used for photogrammetry has been a collaboration with Kurt Vermeister from Sac State. And he's an amazing artist, and he kind of pays homage to Sopwith's geologic block models by making his own hand-carved, amazing wood block models that show all sorts of different geologic principles, faulting, no faulting, all sorts of cool things. But we collaborated with some other folks back at SUNY New York, so Scott and Nick there that you see in the bottom, and they fed the 3D models into some of their GIS program, gave it, made contour lines and digital. So what's really cool is you end up with a model that can be used online or in person in class if you have the computers available that go along with paper versions. So when you're trying to learn about topography or different relationships, you have the models, you have the paper, and it kind of helps give a geospatial recognition a little bit, makes it a little easier to happen there for folks. Scott went a few steps further, and he also applied different geologic formations or ages to different layers here, and allows students to then try to solve the puzzle of what in the heck happened here. How did all this faulting happen? When did it happen? And it's a pretty slick tool as well. I've currently started using photogrammetric models in classes. I'm letting my students use their phones to create all sorts of cool models. Most successfully so far has been with our stream tables. So they take those stream tables, scan it, and then they hop into Sketchfab, where they'll annotate some of the results of what's happening. So maybe they'll show where they had, cut banks or point bars, different incisions, scales of the size of the pebbles that were moved, et cetera, et cetera. So it's really great for simple and complex analysis for all learners, depending on how good your scan is and how deep you want to go. So that brings me then to, where do you actually find the 3D models? Well, Sketchfab, like you've been seeing, is probably the #1 place. There's a bajillions of awesome models out there. The first link goes to my webpage or my Sketchfab page. It has about 100 models, but there's also Rocks and Minerals here, who's Dexter Perkins out at North Dakota, University of North Dakota. And he put his grad students on, during COVID, basically, bought a new computer and said, hey, let's start scanning all of our specimens. So I think they have about 300 or 400 different specimens. There are museums that scan fossils, all sorts of things that are out there for you. The next one that is a pretty useful resource, in my opinion, is V3Geo, and that's kind of the purpose-built for geoscience education. Models that have descriptions on them. When you upload them and contribute to the community, you describe what the heck's going on. But a lot of these, not all of them, but a lot of them are more focused on larger landscapes. And so like drones flying over and putting together these huge, like here's an intrusive dike here that was cutting across a bunch of rocks. And you're like, well, that doesn't look super impressive until you look at the measurement tool over here. That little orange line that I've just drawn is about 600 meters, 650 meters or so. So this is a huge landscape that you can go fly through, and the more you get to it, it'll load more high resolution pictures. But basically, it's another way of using quantitative tools to figure some things out. And then the last tool that I've never really used, but is pretty important for a lot of folks, is called Lime. It's kind of the big brother to V3Geo, and it's pretty impressive. You can overlay formations, all sorts of things like that. But again, that's super advanced. So concluding thoughts, photogrammetric models, they're extremely powerful tools, but they got to be used wisely to achieve user engagement. And it takes a lot of thought and planning at the beginning to figure out, how do you want your students to interact with these things? So they can be used by most learners, especially if you give them age-appropriate tasks and inspire collaborative investigation and sense-making. These models are awesome. So I guess the big thing is, what stories do you want to tell? And if you need help trying to figure out how to help tell those stories, I'm always here for you. So please, if you have questions, ideas, please reach out. I'm here to help, and thank you very much.
Lastly, we will hear from Erin Lyons, who will discuss how photogrammetry is used to make structure for motion models of coral reef environments.
Hello, my name is Erin Lyons, and I am a Marine Researcher 5 with Cherokee Nation Systems Solutions, contracted to the United States Geological Survey. Today we are going to discuss a variety of structure for motion projects that we conduct in coral reef environments at the USGS. First, let's talk about a few common terms that are used interchangeably in the field of SFM that can cause some confusion. Photogrammetry is simply the act of taking measurements from photos. This can be done in a single scaled image or with multiple images. Structure for motion is using multiple overlapping images to create 2D and 3D products. SFM photogrammetry is the combination of the two, or the use of 2D and 3D products built from overlapping imagery to make measurements. These terms are commonly used interchangeably in the field to talk about the use of SFM products to quantify and measure landscapes. There are a variety of coral reef projects at USGS that use structure for motion. We are going to first talk about the large-scale projects and finish up with some of the smaller-scale projects. Our first project uses the SQUID-5, which stands for Structure for Motion Quantitative Underwater Imaging Device, a towed surface system outfitted with 5 cameras that tows behind a boat and continuously collects 2D images. This method surveys entire reef sites. Imagery is collected from the surface, so the image quality tends to be less than some of the smaller scale SM projects that we conduct. But this is a trade-off for being able to sample a larger survey area. We use the orthomosaics and digital elevation models predominantly to measure the structural complexity of the reef. The DEMs give you a precise height measurement. The image in the top right shows the higher elevation of the reef in red. We also use orthomosaics to measure percent cover of reef species in order to answer biological and ecological questions. We can also use multiple surveys over an extended period of time to see how the reef and seafloor elevation is changing. Medium scale structure for motion project. Imagery is collected by divers swimming 1 to 2 meters above the reef with a handheld camera setup. These camera systems can be as simple as a GoPro or point and shoot, to be more complex like a DSLR camera. We survey permanently installed transects, usually 10 to 20 meters long. This imagery has been collected consistently for about 10 years to assess change over time. The image on the far right shows one of our transects monitored in 2004 and again in 2019. This project has a smaller survey area but higher quality imagery. We use these products to calculate the change in reef height over time, which we call bioerosion, species composition, and percent cover. We assess the orthomosaics as part of calculating overall carbonate budgets for reefs. We can also use them to assess disturbances over time, like coral bleaching, coral disease outbreaks, hurricane impacts, and other things. This picture just shows some of the things that we can measure from the imagery. You can see here we can monitor coral restoration outplants like Acropora cervicornis or the staghorn coral, and a variety of boulder coral species. We can also classify fish and sponges to the species level and quantify their size. This type of data is useful for a variety of things like creating population assessments, assessing the efficacy of coral restoration projects, and calculating carbonate budgets on reef, just to name a few. In our small-scale structure for motion project, we are using SFM to measure growth in individual corals. This study has traditionally used a buoyant weighing method where corals are removed from the water to be weighed and measured. SFM will be able to replace that methodology without removing corals from the water. We can also make more measurements, such as surface area and volume, that we have not been able to measure before without harming corals. And you can see here, this is just a 3D model that we've created of one of our individual coral colonies. So, in summary, SFM is opening a lot of doors in marine science, like being able to survey in new locations. We are also able to measure and collect data after the fact, not just in the field. We can take the same measures over and over again, which helps improve accuracy and reproducibility. Accuracy varies depending on the model image quality, but we have been able to get our models accurate within centimeters or millimeters. We can help eliminate surveyor bias by having multiple people measure or quantify data from the image collected in the field.
Thank you, Erin, for sharing work being done to model coral reefs. We appreciate the time all our speakers took to share their expertise on the use of photogrammetry in the geosciences and in earth science classrooms. Thank you for joining us today.
Good afternoon. I'm Lindsay Mosa, and I'm an education specialist with AGI.
And I know we only have a couple minutes left in our webinar today, but we do have our speakers with us who are able to take some questions if you have them. I see that Ryan has been busy answering in the chat, so thank you for that. I do see one question that I don't think was addressed. Oh no, you put your email in there. So that'd be great if the other speakers would like to also provide their email addresses, although I won't pressure you to. But just to get the questions started, what do you all consider to be the limitations of photogrammetry? And are there other technologies that you use in conjunction with it that might help address those limitations?
I'll let the actual researchers answer that one.
Yeah, I mean, I can say that in our research, we've found great challenges dealing with vegetation. Yeah, that's just one thing where photogrammetry is going to capture the outline, the 3D shape and geometry of a plant. And if I just rock surface, for example, an arch, and there's a tree on it, then I have to deal with that later. And there's lots of tools that can be used to deal with that. But that's just something inherent to photogrammetry.
I would say for hand specimens, it's glare, a very shiny surface. Lustrous surfaces are kind of a big pain in the behind. We're working on some new ways with cross-polarization of lighting sources to maybe eliminate some of the glare and the reflection, but it's still not as great. So you can't, it's unfortunate. You can't take really cool pictures of highly reflective like ice or anything like that, or, some really highly reflective, glassy mineral surfaces. Kind of makes it a little hard sometimes, but there's workarounds. We're trying to figure things out.
Yeah, I'm going to agree with both of what they just said, especially in the underwater world. I think photogrammetry is a new up and coming technology because of the limitations with water. As Jeff was speaking to with vegetation, we have a lot of difficulty with moving things. So underwater, everything moves. The vegetation, the fish, all that kind of stuff can cause problems in your models. So that's one thing we're working through. And then issues that come with different water qualities and different light and brightness, clouds, waves. So there are a lot more limitations, in the underwater world than you get on land. But as Ryan said, the technology is pretty quickly advancing. So we're finding new ways pretty much every day to overcome some of those issues.
Great. And I see another question just posted in the chat. Do you have any opinion on open drone maps such as an SFM software compared to, I'm sorry, I don't know how to say this, Agisoft or Pix4D?
Let's
So open
I
drone.
I don't deal with drones, so somebody else, Jeff might be able to answer that better.
I don't know. I wish I did. I mean, we use Bentley's context capture a lot, rather than Metashape. Pretty equivalent. It's just a matter of what license we have here at the university, but I don't know the map. I'm sorry.
I also do not. You can't really use drones underwater. Although we do have AUVs and some autonomous abilities, but not anything specific to drones. We mostly just use Agisoft, and kind of like Jeff said, we have some licensing issues inside of the U.S. government that we kind of get set to. We have to use very specific things. I've used a little bit of Cloud Compare, and I believe that's a free open licensing software. But we more so use that to just compare models that have already been created. So most of our model building, we do use Agisoft, which is not an open source license.
All right, great, thank you. And then do you foresee AI technologies being able to help address some of the issues with photogrammetry, such as motion and glare, like you spoke about earlier?
Boy, I haven't been keeping up with, I'm an expert in that, but I know I've been reading some things about NERF and some other, basically kind of other AI type things that are trying to help fill in the blanks, at least in the real estate version of making photogrammetry images for like walkthroughs and things. And it's pretty impressive. There's another new thing called Gaussian splatter coming out that basically creates a three-dimensional scene around the object as well. So it makes it more realistic and not just the model. But yeah, I think those are, I'm not sure how much AI plays a role in those things, but it's getting pretty crazy pretty fast.
I also cannot speak too much to about what AI is happening out there, but we are using some human in the loop machine learning tools to just help with classifying our models and doing some of the like identification on models that have already been created. I think the biggest thing that we run into with any sort of automation, and I'm assuming this is also going to go for any sort of AI tech when it applies to photogrammetry, is just the computation time that it takes for softwares and computers to go in and to do this type of processing. I mean, it obviously takes a human a long time to do these things too. But a lot of that is limited to, you have to have a big enough computer and processing capabilities, and that starts to get very expensive. So I'm sure that one day AI will be there, but I think right now there are definitely some limitations with just the size of imagery that has to get processed through machines in order to get that kind of stuff accomplished.
Great, thank you. And I think this is our last question here, and I believe it's for Erin. How do you overcome georeferencing issues in underwater photogrammetry?
That is a great question. We definitely have had some of those hurdles before. So it depends on what project we're working on, but some of our smaller transects are permanently installed. So we do have GPS coordinates for, the start and the finish on those transects, and we can kind of overlap them over time. And then stuff like our tow behind vessel, we can actually attach GPSs to those. And so you get live GPS information with, the imagery that's being collected. So there have been some of our older imagery that was collected back in the early 2000s. We don't have that GPS information that goes along with it. And so we've kind of been trying to find some loopholes and some ways to stack imagery on top of itself and use the associated like current GPS information. So we've been able to do things like identify specific coral heads that have been alive or been in that image for, the entire lifespan, and use those reference points to stack imagery on top of itself. So yeah, some of the time we don't have GPS information, but as the technology's gotten better, we've had more and more opportunities to be able to georeference some of that stuff. So it's getting better.
Very nice, thank you. We appreciate the time of all of our speakers today, and if anyone else has questions for us, I know some email addresses have been shared, but you can also email us at webinars@americangeosciences.org, and we will forward your questions on to today's speakers. And then also the recording of this will be posted within the next week on our website as well as on our YouTube channel. And we wanted to share information about the last 2 webinars in the series. So coming up tomorrow, we have one on critical materials and specifically looking at some educational resources for how to bring the skills and careers about critical materials into classrooms. So again, thank you so much for all of your time today, and thank you to our speakers.